Welcome to Hydrology, Hydraulic Routing of Water Flows. This is Chapter 11, Lecture 3. I'm Dr. Marty Matlock. Let's get started. As we've seen in previous lectures, the management of floodwaters requires routing of those flows. And routing of those flows seems to be complicated, but it's really not. It's about recognizing the water balance in the watershed, understanding the water cycle, and then understanding the time value process of water flow, the time dependent process of water flow. We can see water flows all across the landscape at all times, and those flows are increasing and decreasing based upon precipitation events. So you can imagine this process as over a continent, as you see in the diagram, as simply sort of the pulsing of fluids through the system, not unlike blood flow, as it flows to the ocean, the heart of the planet, and it is recirculated through evaporation back to the atmosphere, where it is precipitated onto the landscape and accumulated through the capillaries of small streams and channels into the arteries of major flow systems back to the heart, the ocean. So that cycling is over fast periods of time, is very pulse-like. You can see the hydrographs illustrating that. What we are doing is we're trying to understand the impacts of this flow system through our landscape and to manage them so that we have both water resources available when water resources are needed during times of drought or scarcity, and to ensure that we do not have excess water when we have flood events, so that we can avoid damage to the floods. You should be very comfortable with the cross-sectional area and the ontology of streams by now, the width, depth, wetted perimeter, and area. You should understand these pretty intuitively at this point. You should be very comfortable with the fact that we can always predict flow if we know the area and velocity, and we can calculate the areas based upon assumptions or based upon known characteristics, and we can calculate velocity based upon measurements or based upon primary characteristics of the landscape, including using Manning's N for resistance and then slope. We know that flow moves through channels through in a wave, and that flow is can be through translation of waves, where the wave is where the peaks just are maintained and the width of the hydrograph is maintained as it moves downstream. Or attenuation, where there's channel storage, out-of-bank storage, which is more common. And then in most cases, in most rivers, it's a combination of both. Excuse me. We can calculate the energy of that flowing water by understanding its potential energy. That's the gravitational potential, Y2 versus Y1, and its momentum. It's the kinetic energy, AV squared 2 over 2G, compared to AV squared 1 over 2G. We also understand that the flow through the channel, especially out of bank, is dominated by characteristics of the channel itself. And those cross sections for conveyance are absolutely critical for predicting velocities in the various sections of the river. Those velocities will differ based upon the resistance. You do not have uniform velocity across this system because you have, and anyone's ever watched a river from the banks, especially at flood stage, has seen this. You've seen this sort of slow eddying waters up near the out-of-bank pools, and then in the main channel you see the currents ripping through. The deeper waters tend to be subcritical. The shallower waters tend to be supercritical. That is, the deeper waters are driven by gravity, and the outer waters are driven by, or the shallower waters are driven by momentum. We route our water using flood routing, flow routing, stream channel routing, and reservoir routing. Those 4 routing methods we talked about in a previous lecture. It bears repeating that flood routing is for determining time and magnitude of a flood wave. That's peak flow. Flow routing is a method for predicting the changing magnitude, speed, and shape of a flood wave as a function of time at one or more points along the water course. Stream channel routing, which we're mostly concerned with, is mathematical relationships that calculate outflow from a stream channel once inflow, lateral contributions, and channel characteristics are known. And then reservoir routing is the movement of water through a reservoir and spillways. We do all four of these, by the way, and sometimes we do all four of them in a single project. The movement of a flood wave down a stream system may be described in terms of translation and storage, as we've discussed. You've got to understand that those two things are happening simultaneously. These represent characteristics of two general classes of natural flood waves. We know that translation involves the same hydrograph moving downstream. Storage attenuation involves valley storage or bank storage to reduce the peak flow and change the shape of the hydrograph. So we can have either the flood wave or the attenuated wave or a combination of both. And the difference is the combination of both tends to move the peak flow event down time, as you see in the attenuation. So the more attenuation you have, the more peak flow just moves downstream. And the more translation you have, the more peak flow moves downstream. The more attenuation you have, the more the curve flattens out. So they're not mutually exclusive. Flood wave exhibit both characteristics. The two characteristics describe the upper and lower limiting conditions of the flood routing in a channel reach when considered individually. For example, the upper limit of flood routing is translation to the peak discharge with no attenuation as the flood moves downstream. If storage effects alone act on a flood wave, the result is a maximum attenuation, so the peak discharge may not be further attenuated. This concept represents the lower limit to the flood routing of a channel reach. For these two characteristics of natural flood waves, translation and storage are represented by the conservation of mass and conservation of momentum equation. Conservation of mass equation, sometimes referred to as the continuity equation, is a mass balance and represents storage effects. It states that inflow minus outflow is equal to change in storage between two locations and between two moments in time. The conservation of momentum equation derives from the same basic equation of physics, which states that the force equals mass times acceleration, arranged in terms related to movement of water in a stream such as discharge, end area, depth, width, etc. The solution to these two equations represent the hydraulic routing method. Solving these equations for the extreme conditions of pure storage and pure translation, the two extremes, provide the lower and upper limits of downstream peak discharge respectively. Most flood routing situations are combinations of translation and storage. By solving the conservation of mass and conservation of momentum equations, the most physically based solutions are reached. Hydrologic flood routing methods use the conservation of mass equation with simplifying assumptions to reduce the conservation of momentum equation to a relation of discharge to storage. The primary assumption is that acceleration terms are negligible with respect to other terms in the equation and are ignored. In many flood routing situations, it's a reasonable assumption. The acceleration terms are relatively small for slow rising flood waves on moderate gradient streams. Now, this does not apply to fast moving waters in flashy systems. So be mindful of that. For small to mid-sized reservoirs, the assumption of a level pool is reasonable, and the conservation of mass equation along with the relation of discharge and storage is solved. We assume that after a flow event that you have translation, that the water doesn't stack up on one end of the pool, that it's not coming through so fast that you have this big wave that's standing on the outer side, you see it come up slowly. So it's subcritical flow. For channel and valley flood routing applications, we use the Muskingum Cunge method for flood routing, and we'll describe that. It's a method classified as a hydrologic method because it requires a relation of discharge and storage. This relation is normally developed from steady flow water surface profiles, but may also be developed from a solution of Manning's equation for cross-section. So reservoir routing, elevation storage relationships is one of the most important processes we engage in when we design reservoirs. So you need a elevation of stage with volume of storage curve. So for reservoirs being constructed, elevation stage information is needed from the lowest elevation of the center line of the dam up to the elevation slightly higher than the expected top of the dam. And that's just a function of the geometry of the land above the reservoir or the dam that's being built. For an existing reservoir, elevation stage information is generally needed from the elevation of the permanent pool, principal spillway, up to an elevation slightly higher than the top of the dam. Because this thing's already full of water at the permanent pool level. And so, frankly, that's the only storage you have is from the top of that water up to the spillway. That's the storage you have. Presence of residential rural development, so an increased risk factor, may influence the accuracy needed in development of the elevation storage relations. We talked about dam failure in the previous lecture, and so you saw the challenges with constructing these systems in such a way that they don't fail, because the failure results in death or damage to property. Elevation storage curve is developed using a topographical map or digital elevation model to quantify the volume available for storage at each stage. And we have computer programs that do that very well, including HECRAS. So we can see a type of elevation storage at a reservoir site here, where at elevation of 570 feet, you have no surface area. That's the bottom. Then from 570 to 572, the 2-foot difference, you have a surface area of 9.64, which means that you go half of that is the surface area at 1 feet. Surface area in acres, the average surface area between, you just average the two, 0 to 9.64 gives you 4.82. That's an increment of 2 feet of depth. They have a storage increment of 9.64, which is an acre per acre feet. An accumulative storage, which at 2 feet of depth is 9.64 acre feet. So you come up to the next step, 2 feet higher at 574. We have 27.09 acres of area. So the average acre surface is the average between the two of these. And that's a 2-foot increment of depth. And so the storage input here now is 2 times 18.37, which is 36.73, rounded down, and so forth. So you end up with 9.64 plus 36.73 gives you 46.37. And so it carries forward until you have a stage discharge or stage storage curve. And that stage storage curve looks like this. As elevation goes up, so does storage capacity. This should be starting to look familiar to you, because this is kind of what most of our curves look like. Stage discharge, stage storage. They tend to take on this parabolic look. Second important item needed for reservoir routing is the relation of elevation of stage with discharge through the principal spillway, auxiliary spillway, and over the top of the dam if overtopping is anticipated during the routing. And if it is, you've pretty much done a bad job as an engineer. Select a set of elevations starting at the elevation of the lowest outlet and ending with the expected maximum routed water level, and calculate the discharge at each elevation through single or multiple spillways, and that's how we get Q out. The elevations selected should be the same as those for which the elevation storage relations have been developed, as we just saw, so that you don't have to interpolate as much. The end result will be a table of elevations with the appropriate storage and discharge. So reservoir routing procedures may be used for channel reaches under certain circumstances, because it's the same process. Reservoirs are just real slow-moving streams. An example is a floodplain where a road or railway backs up the water. So anytime you come to a road crossing, basically the bridge abutments serve as a spillway and can back up flow. The decision to treat such a floodplain area as a reservoir requires judgment based on each case's physical characteristic. Is the floodplain relatively wide and the bridge or culvert restrictive? Does it actually restrict flow? Sometimes it doesn't. Does the history of flooding in the area indicate significant storage of water? And that's pretty easy to tell. You go to the bridge and you look around up on the upstream side. You look for flood debris in the trees or on the banks. Could the situation be treated as a reservoir without overtopping occurring? Is the slope of the stream and floodplain flat enough that the backwater will extend a significant distance upstream? Does enough storage in a combination of depth, width, and length exist to significantly impact routing of the inflow hydrograph? All of those things suggest that you can use, if so, suggest you can use reservoir routing at the bridge or railroad abutment. A rule of thumb is if the volume of storage is more than 10% of the volume of the inflow hydrograph, it should be treated as a reservoir. That's pretty simple. So here's a discharge curve for channel reach. So you have storage for each discharge. So you can see that at 1,000 cubic feet per second, you have storage of 1,000 cubic feet per second hour. That's a typical discharge curve. As you move up, higher discharges, you start to get a little less storage per unit discharge. Storage is saturated. If the third important data item needed to complete a reservoir routing is an inflow hydrograph representing discharge coming from the contributing watershed, and you should be very comfortable building these by now. This hydrograph may represent the hydrograph from any of the various flood return periods, a hydrograph from the actual event, any number of sources. Base flow, if any, is generally added to the inflow hydrograph. What we talked about is quick return flow, too, in the previous lecture, coming from streams and seeps, as a constant value in the reservoir routing starting at an elevation where base flow will pass through the principal spillway. This elevation may be derived from the elevation-discharge relations developed for the spillway. This leads to the continuity equation. It's used in reservoir routing for the conservation of mass. For a given time interval, the volume of inflow minus the volume of outflow equals the change in volume of storage. So for any unit of time interval, T1 minus or T2 minus T1 in hours, the time of the beginning minus the time of the end, or time of the end minus the time of the beginning, to give you a positive number. Average rate of inflow minus the average rate of outflow for that time period gives you the change of storage for that time interval. Easy enough to calculate. So we can empirically determine the storage in the systems if we can measure inflow and outflow. If not, we can estimate it. So we can expand this with other variables, and so we have the first over delta. It's basically taking the average of I1 input plus input 2. If we have 2, then we divide time by 2 minus the average output equals change in storage minus 2 minus change in storage 1. So this is a simple way to evaluate multiple inflows and outflows. Now the units we use here, English and metric units for inflow, outflow rate, inflow volume, and outflow volumes, and storage volumes are pretty much all over the board, from cubic feet, inches, cubic feet per second hour, cubic feet per second day, because storage volumes is a double rate function. It's L3 over times 2, T2. And so the same with, and then it's also measured just in terms of acre feet. And then per inches, if times the area. So that's another way. You just have to understand, if you're given the storage volume in inches, then you multiply it times the area to get volume, and then you have a time weighted factor. Same with the metric units, cubic meter second hour, cubic meter second day. You have to understand what the units you're calculating are. Don't let the units mess you up in order to make sure you get you're using the right equations and the right coefficients. The inflow hydrograph of figure 17.6, which we'll see in a minute, is routed using a storage-discharge relationship developed for a stream reach. The steps to calculate the routing are: prepare the storage-discharge relation for each reach. The reach in question has several cross-sections, which may be weighted as in table 17.2, which you can review. To determine the weights for each cross-section, use the distances between them compared to the total lengths of the reach. In table 17.3, the weight for subreach 1 to 2 is 1,000 over 10,000 equals 0.1, and so on. So working curve, tabular plotted of output 2 against storage 2 over for the unit of time plus output 2 over the unit divided by 2 is necessary for solving the equation. Storage indication method has the characteristics that the outflow begins at the same time as inflow begins, so the inflow at the upstream into the reservoir channel passes instantaneously through the reservoir channel regardless of the size or length. This is a simplifying equation, because otherwise you get into minutes, hours, minutes, seconds of breaking this apart, and then you get smaller and smaller intervals, or integrals of time, and before long it just overly complicates, and it's frankly just unnecessary for our assumptions. So it does not cause significant problems in channel routing if the ratio of time of travel over time to peak is about 0.5 or less, where time of peak is the time to rise to peak of the unit hydrograph. So generally speaking, this is okay. We know travel time for the water to travel the length of the channel reservoir is usually at bankful steady flow, and we know that that's length times area into the discharge over 3,600, which takes seconds into hours, times Q, and that's how we have time of travel. So that becomes length equals 36, or total time of travel equals L over 3,600 divided by 3,600 V velocity. And so we end up with a hydrograph with a peak time of 2 hours, time of peak, and an inflow comes in at time 0 and returns back at base flow times 6. So duration is 6 hours. Time of peak is 2 hours. By the way, this is the way you build your hydrographs. You have 3 data points. You have starting point and time and peak flow. You have time of peak. That gives you this triangle. And the area under this triangle is 1/2 base times height. And then time of peak and total duration minus time of peak, which is from the time of peak to the end of the storm. That's the base 2 times the height, gives you the area under the curve here. And if the area under the curve, if you quantify these areas and it's much larger than the total Q after a 6-hour event, you can reduce this slope by simply bringing this triangle in and adjusting it until the area under the curve, and you can do this in Excel very easily, until the area of the curve aligns with your Q. Typically the rising limb is more linear than the falling limb. Falling limb tends to be more parabolic. Now there are double triangle methods for doing this. Back when we had to do all this mechanically or manually, now you can simply adjust your areas adjust your units for each time the units discharge until you calibrate your hydrograph to total volume of flow in the falling limb. So these are the tables we were talking about. So we have cross-sectional separational distance from section 1 to section 2 is 1,000 feet. The total section is 10,000 feet, so that gives us a weight of 0.1. Section 2 to section 3 is 6,000 feet out of the 10,000 feet. That's a weight of 0.6. You guys are good at weighting, length and area weighting. So if we look at outflow, O2 in cubic feet per second, over storage for each of the unit time plus outflow 2 for each of the unit time. So what we're doing is we're getting a relationship between outflow and storage here. So line of equal values. If there is no storage, this is what it looks like. If outflow and outflow plus storage are equal, then this is what the line looks like. If they're not, then you get a different shape, and the outflow tells you that you've got a storage function. That's your outflow, and the outflow plus storage is different. So that's the key to try to quantify the impact of storage on your system. We're used to these sort of time step analyses at this point, where you have inflow, average out inflow, and then we have storage 2 over delta 2 plus outflow 2 over delta 2, and then you have outflow. And so you interpolate, and you can develop these routing tables for calculating, for the example of 17.1. What that allows us to do now is to start building our time step of flow through our systems, where we have inflow and outflow, and that's what we're calculating, building these inflows to outflows, and to calculate the storage effect as we move through our outflow calculations. As Dr. Tom Hahn, one of my best hydrology instructors, taught, this should be intuitive to the casual observer. If this process isn't intuitive to you, try to work through and understand the numbers. That's the best way to understand the process. And so you end up with an inflow hydrograph and an outflow hydrograph. And you can see this looks like an standard attenuation hydrograph, where peak flow is reduced significantly to about 3,800 from 5,000 cubic feet per second. And that duration extends from 6 hours to 9 hours. And the time of peak goes from 2 hours to 3 hours. So you can see that represented here. Here's our actual outflows as we move 290 up to a peak of 3,827 at 3 hours, with the inflow peak at 2 hours at 5,000. Oh, I see. So this table is just a continuation of this table. I had to cut them in two in order to stack them in this one slide. And so this is starting at 5 hours, 4.5 hours to 5 hours. This extends it all the way to 6 hours. Basically, we're back at base flow. Maybe at 9 hours, we're back at base flow. So from 0 to 9 hours. So the storage indication method, which we saw earlier, is also a way to do stage versus storage relationships. And it's just based upon available area for storage. It's based using a contour map or a digital elevation model with a spillway hydrograph. So if we know at a given stage we have an amount of storage, we can then just allocate that directly to the storage. We know that when the water is 6 foot deep, a certain portion of the water is going to be in the outer banks or in the reservoir. And we know the area of that reservoir, and we can average those up as we discussed with reservoir routing. But we have to know our spillway characteristics because we have to know how much water is going out at every step of the way too. So this is elevation storage data that we saw earlier. So the elevation discharge relationship is required. It's used in the two systems. So column 1 lists elevations. Column 2 and 3 show the discharge for first stage weir and orifice in cubic feet per second. Column 4 and 5 show the discharge from second stage weir and orifices in cubic feet per second. Column 6 gives the total discharge of the principal spillway system in cubic feet per second. So here we have our discharge, and so you see our discharge for elevation is quite different because we have here a weir with an orifice, a weir with an orifice, and then a total discharge. So first stage discharge, second stage discharge. And this allows us to control and to add the values based upon stages. And we just add those up in order to get total discharge. And you see the cumulative discharge takes on this completely sort of non-linear relationship based upon these cumulative discharge designs. This is the fun part of engineering, is when you get to design these systems and stack these things in at different elevations or stages and say, all right, we want to drop more water once it hits. We can't let water get to 610 feet, for example. So when water gets to 588 or 587 feet, we're going to put in another orifice, and it's going to create another culvert that'll create another discharge rate. So now that we've got a plot of our two-stage principal spillway elevation versus total discharge for our system, we can route flow through this system using the storage indication method, which is a matter of calculating the time-based storage for each stage. Now we have to take flow-based, elevation-based storage, which we have here, an outflow, and we have to then extract from this the variables we need in order to do the storage indication method, which we saw earlier. So we take each of the stage depths that we have, and we have the discharge rates for each of those stage depths, and then we have the storage that we calculate, and then we start calculating the variables. Output squared for output 2 over 2. If we're going to take this as a half day, what's the storage 2 divided by a half a day? What's this? And then we take storage 2 divided by half a day plus the output 2 divided by 2. And so these are just all variables to build our table. And then if we're going to say, what if this time step is 0.1 days for storage 2 over divided by step in time, and we can see that it increases by a factor of 10, the storage. And the same thing for S2 divided by delta 2 plus, then we just add these up and we come up with these storage equations. These are variables that are not particularly meaningful to us at this time, but then we add those into this table where we have time going from 0 to 10 hours or days, and then add that out for days. and we have our inflow, average inflow, and we have these variables we've calculated in cubic feet per second, S2 over delta 2 plus O2 over 2. And then from that we can calculate outflows. And you can see the way we calculate these. We add all these up, this plus this minus this equals 0. So here we have 35 plus 0 minus 0 equals 35. Here we have 74 plus 35 minus 3 equals 106. And then that gives us, and so here we have 82 plus 106 minus 9 gives us 179, and so forth. And so we just keep ratcheting down our lists and interpolating to the extent that we have to, and ratchet down our list. And that's the way we create the outflow hydrograph. Now, it seems convoluted because it's a time step forward filling in a back time. That's because it's mass balance based with an understanding that what's stored in the watershed for this time interval will come out of the watershed next time interval. And that's why you calculate forward. This is tedious. That's what engineering is. You just got to practice it. I can tell you that I know what the keys on a piano are. I know what the notes are. I know where middle C is. I know what range of notes the left hand should play and the right hand should play. And I know how to read music. That doesn't make me a piano player. The only way I'm going to be a piano player is to take what I know and practice, and practice, and practice, and practice. Taking what you know here and practicing is what differentiates you from a student to a practicing engineer. Ultimately, this is what you're going for: inflow and outflow hydrographs. Notice how flattened out that hydrograph is. That's the attenuation effect of a reservoir. That's why we build flood control reservoirs. Without the reservoir, flow through that channel for a given rainfall event would be 200 or 2,000 cubic feet per second. And let's say at a given discharge curve, that would be 20 feet deep. Because of the attenuation, we have the same volume of water moving out because you can't change the mass. The mass is there. The mass is neither created nor destroyed. It's conserved. But we spread out that peak as it goes over that dam spillway, so it never really peaks. It peaks at about 3,500 or 350 cubic feet per second maximum, which would be, relatively speaking, instead of relatively shallow water. It doesn't flood downstream. Another way to do this is using the Muskingum Cunge channel flow routing method. So you got the reservoir routing method we just saw. But what if you can't use that? Well, the Muskingum Cunge channel flow method, here described by the Army Corps of Engineers, is another way to do this. And this is just another storage staging process, usually kind of the same process. Remember, all we're talking about is water moving through a channel. Don't let this get overly complicated in your head. We just have to build columns of numbers in order to stage the water in a spreadsheet so that we can not lose it, not destroy it, not create it, make sure we maintain conservation of mass, but move it through in a time-preserved way. So this is really spreading water out over time, because that's ultimately what routing is: spreading water out over the landscape or down the channel over time. The Muskingum Cunge method is a modification of the storage routing method. It considers the attenuation of flow where inflow to reach is greater than outflow. The differential flow creates a wedge of storage above a uniform flow rate corresponding to the downstream flow rate. This is for channels, not for reservoirs. To address this non-uniformity, it uses a linear storage assumption, basically taking the downstream and upstream gradients and making a linear assumption about storage through the system. And then it interpolates that or integrates that to a middle point through the reach. So S is the storage equals K times XI times that's input plus 1 minus XO, where K and X are functions of channel flow, I is inflow and O is outflow, S is storage. Conceptually, it's just a linear regression equation. So if we look at this equation more detailed, storage equals K, which is delta X over C, and in this case, X equals 0.5 times 1 minus peak flow rate divided by channel slope times 5/3 V times reach length, delta X, So that's you need reach length and channel slope to calculate, and peak flow rate. It's all you need to calculate X. By the way, that X is different than delta X, which is the reach length. So I tried to italicize this X. So don't confuse the first X with delta X. So I didn't get it italicized. I see in the second representation of the X, the XI plus 1 minus XO. But that's just a way to calculate storage. So that's all this X, which is a function of storage, or channel slope, and reach length, and peak flow. And so it assumes a certain amount of storage. And then velocity is V is velocity of bank full. So C equals 5/3 V in this equation. There's nothing complicated about this. It uses all the same relationships we had before to come up with the storage level rate. That storage rate is a function of attenuation of flow over time. Think about it as a runoff abstraction, as the same thing as the runoff abstraction. And in fact, that's kind of where the concept came from, because these hydrologists use the same tools. So outflow 2 equals some coefficient 0 of inflow 2 plus some coefficient 1 of inflow 1 plus some coefficient 2 of outflow 1. And so the coefficients of 0, 1, and 2 are seen here, minus kx plus 0.5 delta t over k times I minus x plus 0.5 times delta t. These are all curve fitting coefficients. They give you a polynomial curve fitting relationship. And so you see all the relationships C0, 1, and 2. And these are proportionalities. We're basically taking inflow 2, inflow 1, and outflow 1, and we're proportioning them to get outflow 2. And these proportions are all based upon the relationships of inflow, x, and delta t. So you set the routing period delta t, and by the way, x is this. X is a function of peak flow rate, storage slope, and velocity. Nothing complicated. This just allows you to proportion them out, because when you do all this, you should have a proportioning that ends up that all equals 1. So set the routing period such that it is less than time of peak divided by 5. So you have to have fairly short time steps here. 10 minutes is a good starting point. Tabulate storage for each segment inflow over each time step downstream. Calculate each outflow for each routing period. The routing periods are usually tabulated in sequence, so the outflow can be determined for any period over the event. An output runoff hydrograph is constructed from the outflows over routing periods. It sounds complicated. It's really not. You end up with an outflow hydrograph that looks like this. Now, we're not going into more details with this because, frankly, HEC-RAS does this for you. And most of the time, you're going to use HEC-RAS. But if you need to do this, there are examples of this in the literature. You found examples in your reference document. Frankly, we're just short on time for this 5-week class, so we need to move forward. And I want you to be doing the work rather than tediously grinding around in the gears of a spreadsheet to do this work. It's not that complicated. You have resources to review. Again, I've shown you where the notes are. I've shown you where to place your hands. And I've taught you how to read music. Time to practice. Thank you for your attention.